The next thing I'll talk about are subspaces. So a subspace of a vector space is basically a subset, so it's a smaller set that's still itself a vector space under addition and scalar multiplication. However, subspaces are a little bit easier to show. For a vector space, we need to show all 10 of those properties, but for a subspace, we only need to show 3. 1, that the 0 vector is in W, 2, that it's closed under addition, and 3, closed under scalar multiplication. So we can do these 3 things and show that it is a subspace. The first example of a subspace, let's consider the set of symmetric matrices. Well, the sum of symmetric matrices is also symmetric, and the scalar multiple of symmetric matrices is symmetric. So symmetric matrices form a subspace of the matrix space. In the same way, upper triangular, lower triangular, and diagonal matrices are all subspaces. The next example, the set of all continuous functions. So in calculus, the sum of continuous functions is continuous, and the scalar multiple of continuous functions is continuous. And we call this space C, negative infinity to infinity. So the C is just for continuous. Along these same lines, I can consider all functions whose derivative is continuous. And this is known as C1 functions. If I want to consider functions who have a continuous second derivative, that would be C2. Continuous third derivative, C3, etc. The next example, let's start with the space of all polynomials of degree 2. This doesn't form a vector space. In particular, here's a polynomial of degree 2, and here's another polynomial of degree 2. However, when I add them up, you'll see that we end up with 7t plus 1, which is no longer degree 2. So it's not closed under addition. However, we can consider the space of all polynomials of degree 2 or less, because adding 2 polynomials may decrease the degree, but it'll never increase it. Same thing with scalar multiplication. And in general, the set of polynomials of degree n or smaller is denoted by this p sub n. Next, let's consider 2 vectors in a vector space V. We're going to let W be their span. We want to show that W is a subspace. Well, let's start with closure under addition. Let's start with the 0 vector. 0 is equal to 0 v1 plus 0 v2. So that's in there. The next thing is closure under addition. So let's take 2 vectors in there. The first one would look like c1 v1 plus c2 v2, since this is the span. The next one, d1 v1 plus d2 v2. We can regroup this and get c1 plus d1 times v1 plus c2 plus d2 times v2. And we can see that this is also in the span. So it's closed under addition. For scalar multiplication, let's multiply by a scalar and see what happens. So now we have r c1 times v1 plus r c2 times v2, which is also in the span, since this is also a linear combination. So I've shown all 3 things, so this is a subspace. There's nothing unique about 2 vectors. Basically, if you have any set of vectors in a vector space, their span will form a subspace. And my last example, let's let W be the set of all vectors of this form, where A and B are arbitrary scalars. And we want to show that W is a subspace of R3. Well, first I can rewrite this in column form, and then I I can break it up the same way I've been breaking up general solutions. Basically, I'll have an A vector, which is 1, negative 7, 2, plus a B vector, which is 4, 1, negative 3. Since A and B can be any numbers, and if I call these vectors v1 and v2, this is the span of v1 and v2, which we've just shown that the spans form a subspace. So this will form a subspace.